Hello everyone, and welcome to the second part of this lecture. So in the first part of the lecture, you'll recall that we ended up discussing the ratio test and how the ratio test is a pretty cool way of figuring out whether or not a series is absolutely convergent or divergent. And in the worst possible outcome for the ratio test, it tells us really nothing about the series that we're testing. For the second part of the lecture, I want to start by going over another very useful test called the root test, which luckily is based on a very similar idea to the ratio test. So what I'm going to start by doing is going over how the root test is similar to the ratio test, and that it's giving us a measure of how close a general series is to a given geometric series. So we'll start by kind of just getting the idea of what's going on with the root test and what it's telling us, and then move on to writing it down. So consider a geometric series of terms, and just for short we'll call these the kth term here bk. Remember, this is a series of the form a naught times 1, so a naught plus a naught times r plus a naught times r squared, and so on and so forth. If instead of looking at the ratio of subsequent terms, which we looked at last time, we look at the kth root of the absolute value of the kth term of this series, the kth root of bk. So if we look at the kth root of the kth term in this series for large values of k, this is going to behave in a very special way. So the absolute value is going to be the absolute value of a naught times r to the k, the kth root of this, which is going to be the absolute value of a naught to the 1 over k, so the kth root of the absolute value of a naught, times the kth root of the absolute value of r to the k, which is just equal to a naught to the 1 over k times the absolute value of r. So this is, remember, for a geometric series. If we look at the limit of this as k goes to infinity, this is going to be the same thing as the limit of this as k goes to infinity, which is the absolute value of r times the limit as k goes to infinity of a naught to the 1 over k. And this limit is an exponential indeterminate form. It's going to be a constant to the infinity. You can use L'Hopital's rule to go through and show that this is always, for any value of a naught, going to be equal to 1. So our limit here of the kth root of the kth term of this series is exactly equal to r for a geometric series, and we know that this is going to converge then when the absolute value of r is strictly less than 1, and it diverges when the absolute value of r is greater than or equal to 1. And so this whole derivation right here has been just for the geometric series. But the idea here now is that for a general series, this limit, the limit of the kth root of the kth term of the general series, is giving us a measure of how close that series is to a geometric series with that same value of that limit. And thus we can use this limit to tell us whether or not a series is absolutely convergent in the exact same way as the ratio test. For the root test, we consider a general series of terms AK. This is a general series, not necessarily a geometric series. And we look to the limit, this is what we call rho, the limit as k goes to infinity of the absolute value of the kth root of AK. And I'm not going to spend time writing down the conclusions of this theorem, because the conclusions of this theorem are directly the same as for the ratio test. Even the inconclusivity result. So I'm just going to copy each one of these conclusions and paste them right here. I recommend in the notes, when you're taking notes, that you do copy these down, just so you can kind of, get some practice remembering them. But the idea here is that the root test is saying that if this limit is equal to rho, then when rho is strictly less than 1, the series converges absolutely. When rho is strictly greater than 1, the series diverges. And if rho equals 1, then the ratio test is inconclusive, meaning we have to choose a different test. So let's go through and do a couple different examples of this, just so that it's clear how to use this. We'll consider the sum from k equals 1 to infinity of k plus 1 over 4k plus 3 to the power k times negative 1 to the k. So this is alternating series, general series of positive and negative terms. If you go through and plug in the terms in k, the first term is going to be 1 plus 1 over 4 times 1 plus 3 to the power 1 times negative 1. So to the 1 is negative, and it'll be positive 2 plus 1 over 4 times 2 plus 3 to the power 2, then it'll be minus 3 plus 1 over 4 times 3 plus 3 to the power 3, then times, so the negative here is from negative 1 to the 3, which is negative, and then so on and so forth, all the way to infinity. That's what this series is. So this would be a series that if you try to do the root test, or the ratio test too, it wouldn't be super nice to evaluate the limit. So it's much easier to say, look at the limit as k goes to infinity from the root test. So we call it rho, the limit as k goes to infinity, the absolute value of k plus 1 over 4k plus 3 to the power k times negative 1 to the k. The absolute value of this, and we're looking at the kth root of this absolute value. Right, really what I just did here was just kind of plug in the definition of the terms in the series. So it's the limit as k goes to infinity of the absolute value of ak. Now, before we take the root here, the kth root, we want to first do the absolute value. And you'll remember that the absolute value of A times B is the same thing as the absolute value of A times the absolute value of B. And that's nice because here the absolute value of this times this ends up becoming the absolute value of this, which is always positive, times the absolute value of this, which is going to be 1. The absolute value of negative 1 to the k is going to be 1 regardless of whether this is positive 1 or not, because we're taking the absolute value of it. So this is going to reduce to the limit as k goes to infinity of the kth root of k plus 1 over 4k plus 3 to the k. So it's the kth root of this term. And so rho then is going to be the limit as k goes to infinity. Kth root of this to the k is going to be k plus 1 over 4k plus 3. In one application of L'Hopital's rule will give us that this is equal to 1/4, which is strictly less than 1. And so we can say, therefore, by the root test, the series that we started with, or this infinite series right here, will be absolutely convergent. Meaning that the sum of the absolute values for this series converges, and this implies that the series itself also converges. Let's do another example, just so that we can see the full range of possibilities here. So let's consider the infinite series starting at k equals 1 of 4k plus 3 over 3k minus 5 to the power k. And again, this is going to be an ideal root test because we have power of k here, and we know then when we take the limit as k goes to infinity of the absolute value of ak, and the kth root of this is going to be the limit as k goes to infinity of 4k plus 3 over 3k minus 5 to the power k, and it'll be the kth root of that. And I'm not including the absolute value here because there's no positive or there's no negative terms in this series. All of the terms are positive in it. So if we go through and evaluate this limit, this becomes the limit as k goes to infinity of the kth root of this to the power k will just be 4k plus 3 over 3k minus 5, which after one application of L'Hopital's rule will give us a value of 4/3, which is strictly greater than 1. So therefore, this series is divergent, or is a divergent series from the application of the root test. And again, the main idea is that basically what this limit that we're calculating is telling us is that for large values of k, or very, very far into this series is behaving very similar to a geometric series with an r value of 4/3. And we know that if a geometric series has an r value of 4/3, it diverges. So this is kind of the intuitive way of understanding this. Whereas for this example we did earlier, this series right here, the sum of absolute values, when r is very large, this series is behaving like a geometric series with an r value of 1/4, which converges. So this is why this is a very, very, very useful test, and gives us kind of a similar, very, very powerful test to evaluate convergence or divergence. So I want to do one more example, and I'm actually going to do the same example that I did at the end of the ratio test discussion, where I'm going to compare two separate series that we know the convergence state of, the harmonic series, and the p series with p equal to 2. And so when we do the root test on this series, the harmonic series with, or the p series with p equal 1, what we're going to end up getting for our limit rho is going to be 1 over k to the power 1 over k. And the limit for rho for the p series of p equals 2 is going to be the limit as k goes to infinity of 1 over k squared to the power 1 over k. And using L'Hopital's rule for exponentials, because this indeterminate form is a 0 to the power 0 indeterminate form, as well as this one right here. So when we use L'Hopital's rule for exponentials, we get that this is equal to 1, and also that this is equal to 1. Which would be good practice for your limits, and I recommend going through and trying to show that. But that means that for both of these examples, the root test is an inconclusive test. It doesn't tell us anything about the convergence or divergence of these two example series. Luckily, we know that from our previous investigations, specifically using the integral test, that the harmonic series diverges, in that p series converges with p equal to 2, because 2 is greater than 1. But the root test fails for these two examples, and will fail for any p series type example, which is the same thing that we observed for the ratio test. So again, be very, very careful. If you get a limit of 1, it doesn't tell you anything in either the ratio test or the root test. You have to use a different test in order to investigate the convergence. So for the remainder of the lecture, what I want to do is just kind of finish up our discussion on absolute convergence versus conditional convergence, and give you a couple different general tests that will be important for investigating alternating series. So we'll start with the alternating series test, and then move on to a discussion of why absolute convergence really is a much better and stronger thing than conditional convergence. So I showed you before that the alternating harmonic series converges to the natural log of 2, And we actually have a much stronger theorem called the alternating series test, which really actually codifies this for us very, very nicely in terms of a general test. And this says the following. It says that if we have an alternating series, so a series of the form starting at, say, n equals 1 to infinity, where the terms ak are going to be alternating between positive and negative, say negative 1 to the n plus 1 times un. Oops, I'm using n here for my index of summation. So the terms an are alternating between positive and negative values in this case. So it'll be u1 minus u2 plus u3 minus u4 plus u5, and so on and so forth, all the way to infinity. This series will always converge if the following conditions are true. The first condition is that each one of these UNs has to be positive. So this means these terms are generally going from a positive term to a negative term, a positive term to a negative term. That's what this condition guarantees. The UNs have to eventually be non-increasing, which means that UN has to be greater than or equal to UN plus 1 for all n greater than or equal to some integer n. And the last condition comes from the fundamental convergence criterion. The limit of these terms, as n goes to infinity, must be equal to 0. But as long as all these three things are satisfied, we have that any alternating series in this form will in fact converge. So if we apply this to the alternating harmonic series, see that for the alternating harmonic series, the uk or the un, kth term, is 1 over k, and we have that uk, which is 1 over k, is always positive. Um, 1 over k is always decreasing. So it's not just eventually decreasing. The function 1 over k is always decreasing. As you increase k, this thing gets smaller and smaller and smaller, which you can show if you take the derivative with respect to k of 1 over the function 1 over k. This is negative 1 over k squared, which is less than 0. And so this is decreasing. And then lastly, the limit as k goes to infinity of 1 over k is equal to 0. So we say that, therefore, by the alternating series test, this series must converge. And furthermore, I am not going to prove, but I gave pretty good justification for why this actually does converge to the value natural log of 2 in the previous lecture video. And this brings me to something that I want to, a very important point that I want to make out here for conditionally convergent series. And specifically, this is an example of what's called the rearrangement theorem for conditionally convergent series. And we really have two versions of this theorem. One for conditionally convergent series and one for absolutely convergent series. The theorem for conditionally convergent series says that if a given series of AK is conditionally convergent, meaning the sums of the absolute values of the AKs do not converge, then there exists a permutation of, and permutation is a rearrangement hence the name rearrangement theorem, of the terms of the series into a new series of BKs that will converge to, and we'll say this is L. This rearrangement series will converge to M for any real number M, not necessarily equal to L. And this is somewhat troublesome, and one of the reasons why conditionally convergent series are not necessarily super nice. And what I want to do is, I'm not going to prove this because it's a little bit difficult to prove. However, I'll show you through examples how this can be directly true. We wrote down the alternating harmonic series and gave a pretty good explanation of why it converges to natural log of 2 in the last lecture. This series is conditionally convergent, though. Some of the absolute values certainly do not converge. So what the rearrangement theorem is saying is that the order generated by this formula right here for the terms is very, very, very important. So in order to get the natural log of 2, we have to do 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on and so forth, all the way to infinity. This is the only way that we can get the natural log of 2. And what the rearrangement theorem is saying is that for this series and for any alternating series that's conditionally convergent, we can change the order of these additions and subtractions to converge to any real number that we want to converge to. For instance, if I take essentially the same series. And I replace all the negative terms, and this is going to be the same thing as negative 1/2 is the same thing as positive 1/2 minus 1. Negative 1/4 is the same thing as 1/4 minus 1/2. I continue to do this all the way down the series. And so what I'm doing here is just replacing each one of these negative terms in our standard harmonic series by a new term, which is the same as the original term, just a different integer expression of that term. So for negative 1/2, it'll be 1/2 minus 1. For negative 1/4, it'll be 1/4 minus 1/2. For negative 1/6, it'll be positive 1/6 minus 1/3, plus 1/7, plus, make a little bit more room here. Next term here is going to be negative 1/8 in our harmonic series. Sorry, yes, positive 1/7 minus 1/8. The next term here is going to be positive 1/8 minus 1/4. And the key thing here is that if we now consider rearranging these terms, so moving, say, this is going to be 1 minus 1. So you have 1 and negative 1 here. Then you have positive 1/2 here and negative 1/2 here. Then you have positive 1/3 here and negative 1/3 here. Positive 1/4 here and negative 1/4 here. And so on and so forth. The partial sums of this series right here, the first one's going to be 1, the next one's going to be 0, because 1 minus 1 is 0. The next one's going to be 1/2. The next one's going to be 1/2 minus 1/2, which is 0. So this is 0, and then the next term is going to be 1/3, and the next term is 1/3 minus 1/3, which will be 0, and so on and so forth. This is the sequence of partial sums. And this sequence of partial sums has a limit of 0. And this is essentially what this rearrangement theorem is saying. It's saying that we cannot do stuff like this without changing the actual series. So the thing that's wrong here is that it's saying that going from this step right here, or this line right here, to the next line, these two things are not equal to one another, because what the rearrangement theorem is saying is that when we change the order of these additions in the partial sums, the sequence of partial sums, we are changing the thing that the series actually converges to in a conditionally convergent series. So these two things, this sum right here, this infinite series right here, is not the same thing as this infinite series right here, because they converge to different values. And this says for any conditionally convergent series, we can do this. We can rearrange the terms to get any real number that we want, which is a very, very important point and very important to consider when we're considering conditional convergence. Thankfully, we do not have this issue for absolutely convergent series. So for an absolutely convergent series, we have a much better rearrangement theorem. This is why I split the rearrangement theorem into two parts. The rearrangement theorem for absolutely convergent series is the following. So if sum from n equals 1 to infinity of some series an converges absolutely, then for any permutation or rearrangement of terms in the series Bn, the infinite series of Bn is equal to the infinite series of An. So this is why absolute convergence is so special. It basically says that an absolutely convergent series doesn't care about the order in which its terms are added, but a conditionally convergent series does care. It does depend on the order in which the terms are added. And I think this is all that we need to talk about for these two concepts. So thank you very much for tuning into lecture today. I hope you had a fantastic day and that you learned something.